Alrighty, 8.6 molecular structure of acids and bases. So, pretty much as the title implies, we're looking at the structure of these. So, usually the Lewis structure. We could be looking at other stuff, but that's the main focus. And then we're also going to be looking at electronegativity values as well as some other stuff. And you'll see what I mean when we get there. So, the molecular structure will help determine how strong an acid or a base is. We've talked about strong versus weak acids in general, but if we had to compare different acids to each other, we could. So, for example, if we're looking at a weak acid, we can compare the strength by looking at its structure. And so the strength of an acid or base is just based off how it will donate an H plus or an accept an H plus. So it's pretty much the definitions of being an acid or a base. And the way that we know its strength is by stability of the conjugate base or the conjugate acid. And so stability is how likely those conjugates exist as itself in solution. So pretty much how likely is that particle staying that particle in solution. So you have your acid, for example, and so the acid becomes a conjugate base when it donates an H to whoever it's donating to. And so the stability is based off the conjugate base of that acid. So if the conjugate base doesn't accept the H plus from, an acid, then it's very stable. And so if it's stable, that means the acid is a stronger acid, relatively, because we're always talking about relativity when it comes to comparing one thing to another thing. Because, the conjugate base doesn't want to accept it as much. And so that means it's going to stay a conjugate base rather than going back to being an acid. So that's an example. If your conjugate acid is more stable, that means you have a stronger base because the base is acting like a base and it's becoming its conjugate acid, and so the conjugate acid is chilling in there, not acting like an acid as much. So this stability factor that we're talking about is going to be based off structure because obviously this title is called molecular structure. And so we're going to see how that is. And so for a conjugate base, will the conjugate base attract an H+? Will it actually act like a base? Same goes with a conjugate acid. Will that conjugate acid donate an H and act like an acid? And so we're seeing whether or not that actually happens. And so we're going to fill out this chart. Make sure you're paying attention to what I'm saying, not just what's on the chart, because obviously that's how we do our things here. And so we're going to talk about some strong acids, some strong bases, some weak acids, specifically carboxylic as well, weak bases, and then we're going to look at the strength of weak acid as another factor rather than just weak acids in general, because there is something particular about those. So we're going to start off with the first one, strong acids. I didn't list all of them, I just listed a couple. And so it's very strong because the conjugate base is stable. We have this stable conjugate base. It does not want to go back to being an acid because strong acids dissociate completely. So the conjugate base is very stable in solution. So for example, hydrochloric acid, its conjugate base is chloride ion. And that chloride ion is not going to act like a base because strong acid is so strong that it will not reform HCl in solution. And so because this completely dissociates these strong acids, then the conjugate base is going to be highly soluble in solution. It's going to exist as is. It's 100% ionizing. So we have the large electronegativity of the halogen group on the periodic table, for example, like the Cl, the Br. And so that is going to be very important. Another important thing is going to be some other stuff. So we have induction. And so induction, as I've labeled here, are polar bonds that are affecting bonds that are farther away. So it might be 2 to 3 atoms away. And so if I have a polar bond, you can induce a dipole in something that is 2 to 3 atoms away. Or we could just affect other polar bonds in molecules in general. And then obviously we have resonance. If we have resonance in some of these structures, so for example, these polyatomics here, if I were to draw out those Lewis diagrams on those polyatomic ions, then you'll see the resonance, the electrons that are moving around, and since they have the freedom to move around, that also makes them very strong acids. Okay, so for strong bases, just like strong acids, they 100% ionize. If I were to look at the equilibrium solubility of these, it's going to be way bigger than 1, so they're super, super soluble. And so here's the generic reactions for the strong bases. Group 1 is the first one, group 2 being the second one, since group 2 is a positive 2 charge when ionized. And so if I were to look at hydroxide in general, just the hydroxide part, the hydroxide part could act like a very weak acid technically. So that's why you're seeing this ionization of a polyatomic ion here on the right. But as you can see with the equilibrium arrow, it's focusing more on the hydroxide. So the hydroxide is more stable at that point. And so this only corresponds with the hydroxide donor bases. Obviously, we have other kinds of bases, the other kinds of weak bases, so we would think about how the conjugate acid could be an acid for those. Okay. Then we have our weak acids like carboxylics, for example. So here is a carboxylic acid example. So you do learn the functional groups of the various ones for molecules and stuff eventually. For now, here's carboxylic acid. This R here is whatever. It's either carbons or hydrogen and carbons or hydrogen by itself. It's hydrocarbons, essentially. And so you can attach a whole bunch of different molecules here on this R. So that's why it's just generic. That is going to be on future STEM classes you take, so make sure that you recognize that you could replace that R with something else. And this is just the generic form. So carboxylic acid has this double bonded O and then OH attached to the C at the very end. And so you can see here, as the name implies, it's an acid. And you can see that the H over here is donating to the water. And so you have hydronium and then the carboxylate ion. And so again, R is whatever that structure may be. Cool. And so you can see when it's an ion, like this ion over here, technically we have resonance, so you can see how the electrons can be moving around from here to here. You could literally see it back and forth. And again, you'll see this more electron pushing kind of stuff in OChem, whenever you take that, if you do. And so that's pretty much what we're going to be seeing. We see this resonance, it's a stable ion, but it's still not that stable compared to other ions. Cool. And then for weak bases, so we're going to do ammonia as an example right here. And so what determines the strength of this is looking at the various values for these. Obviously, we've talked about ammonia many times, but you can also have nitrogenous bases. So what B is whatever it could be. I should have named it R, but I'd B for base because that's where my brain was at. But you can have any kind of attachment there. So it could be carbons, hydrogens, hydrocarbons, and so on. And so the carboxylate ion here, that is an example of a base. It's a weak base. And so you can talk about the resonance and how it's like kind of stable, but not too stable. And then strength of a weak acid. So this is probably the part that students forget or confuse about. And so you want to think about electronegative elements. So we learned the electronegativity trend on a periodic table increases from left to right and then down up. So the most electronegative being fluorine, and we're ignoring the noble gases. And so in an acid, if you do have more electronegative elements in general, for this example I put here is more oxygen atoms, then we can increase the stability of the conjugate base. And so The stability of the conjugate base is based off induction, which is again the polar bonds affecting bonds that are like 2 to 3 atoms away, and then resonance because the electrons can be moving around. So because the conjugate base is stable, that means it does not want to go back to being an acid because it wants to stay as its conjugate base. And so the weak acid is stronger if you have more of those electronegative acids. So an example of this is HBRO blank. And so all of these structures, well, not all of them, but most of them have some kind of resonance in it with all the oxygens attached. And so as I have more oxygens, that means this acid over here is stronger compared to this one, because those have less oxygen. Again, the oxygens are increasing the stability of the conjugate base. So for example, HBRO3, the conjugate base is going to be without the H, so it'd be BrO3 minus 1. And so because of resonance with the oxygens as well as induction, then that will make the BrO3 more stable as an ion in solution versus BrO2 minus 1 versus BrO minus 1. So it depends on the amount of electronegative elements, the strong ones as they were. So here's an example MCQ. So go ahead and look at the structure and then look at the question and then go ahead and see if you can figure this out. All right, ready? So the answer for this is B. And the reason why is because of the electronegative oxygen. There's an extra one. So you could see it here. There's an extra one. And so we have the extra oxygen, and so there's more stability because of that more electronegative oxygen atom helping stabilize the conjugate base when this H is donated. Because remember, these are acids. So the H is donated, and so the conjugate base would be this part over here for the first one, and then this part over here for the second one. And so that's why that's going to be stable. Alrighty, that's it for this section. Bye!